Hello everyone, my name is Muhammed Esgin, and I'm going to tell you about our paper on post-quantum adapter signatures and payment channel networks. And this is a joint work with Oğuzhan Ersoy and Zekeriya Erkin. So let's first look at the agenda for today. So I'll tell you about adapter signatures because it's a relatively new concept. So I'll tell you a bit about their syntax and formal model, and I'll tell you about what they are useful for. And for our lattice-based construction, the existing formal model is actually not sufficient. That's why we need to extend on this formal model. And I'll tell you about our extended formal model. And then I'll describe our lattice-based adapter signature that we call LAS. And I'll briefly touch on the challenges in the lattice setting. And finally, I will talk about blockchain applications, in particular atomic swaps and payment channel networks. But I don't think I'll have enough time to go into the details of payment channel network, and I'll refer you to the paper for that. Okay, so an adapter signature was previously known as a scriptless script, and this was introduced by Poelstra in 2017, and recently it was named adapter signature by OMR et al., and in the same paper it was formalized. And the main goal of an adapter signature is to address the scalability and interoperability issues of blockchain applications. And in particular, there are various advantages that is brought about by adapter signatures. And mainly, for example, one of them is reducing on-chain costs and improving fungibility of transactions. And also, it gives you advanced functionalities that is beyond the blockchains, or that is not restricted by the blockchain's scripting language. Okay? And it has found some nice applications like payment channel networks, atomic swaps, and discrete log contracts. And the construction of an adapter signature actually extends an ordinary signature. And in addition to an ordinary signature, we also require a hard relation compatible with the signature to construct our adapter signature. So for example, you can think about knowledge of discrete log relation together with a Schnorr or ECDSA signature to be these pair of two tools. And actually, this, although it's called a signature, this is rather a two-party protocol, but the final output is an ordinary signature from a single party. Okay, so if you look at it from the outside party's perspective, they only see that an ordinary signature is output. Okay? And maybe a better name for an adapter signature could be conditional signatures, because the main idea, I think, is basically to embed a condition inside a signature. Okay, so let's see adapter signatures a bit more formally. So let's take an ordinary signature scheme that we denote by capital sigma. Okay, so this has a keygen function, a sign function, and a verify function. And we also take a hard relation. So capital Y is our public statement, and this little y is our secret witness. Okay? And then we will have 4 functions in total, in addition to, of course, these 3 functions that comes from the ordinary signature. So we first have a presign function. Okay? So in this case, a signer takes a message and signs this message using the secret key sk. And of course, the signer, since we need to relate it to this hard relation, also makes use of the public statement y when running this presign function. Okay, so at the end we get a pre-signature that we denote by sigma hat. And then we have a verification function for the pre-signature that we call pre-verified. So this is quite standard. And then a more important function is this adapt function, which now takes a pre-signature, sigma hat, and also the main input here is a witness, little y. And then using the witness and the pre-signature, this adapt function outputs a full signature sigma. Okay? And then the last function is extraction function, which takes this pair of pre-signature and the full signature and then extract a witness y prime that satisfy this relation with respect to the statement capital Y. Okay? So this view, I think, does not really tell the story behind an adapter signature, and I think a better way is to look at it as a protocol. Okay? let's suppose we have two parties, signer Bob and a secretary Alice. So in this case, the secretary means that the holder of the secret Y. Okay. So the signer has a public secret key pair, and the secretary has a statement and witness for some hard relation R. Okay, so they exchange some public information. So the public key is obtained by the secretary and the message as well. And similarly, the signer obtains the public statement Y and the message M. Okay, and then the signer runs this presign function, gets a pre-signature, sends the pre-signature over to the secretary, and then since secretary knows a witness Y, can adapt this pre-signature and get a full signature, and then the secretary basically publishes this full signature sigma, which means that the signer gets a hold of this full signature, and then since the signer also has access to this sigma hat, using sigma hat and sigma, the signer can obtain a witness Y prime for the statement capital Y. Okay, so of course a natural question to ask here is, what's the point? So why do we do this? Okay, so if we ask this question from the secretary's perspective, this means that this pre-signature is like a commitment. Okay? So this is like a commitment to signing the message M, but only if someone who can complete this, and that someone needs to be a secretary who holds the witness to the statement capital Y. Okay, which means that any secretary who gets a hold of the sigma hat can complete or adapt the pre-signature and get a full signature on the message M. Okay, and if we ask the same question from Bob's perspective or the signer's perspective, what this means is that from any pre-signature and signature pair, Bob gets access to a witness for the statement Y, which is essentially what he wants. Okay, which means that if the secretary uses the full signature or publishes the full signature, the signer gets a witness. Okay, which is essentially the end goal for the signer in this setting. Okay. Okay, so if we zoom out a bit and we take this two-part protocol into a box, so what happens at the end of this two-part protocol is that, and we also put into the picture some outside parties, and what comes out of this two-part protocol is just an ordinary signature, which is actually a signature signed by Bob. Okay, and the outside parties only see that Bob signed this signature, and they do not realize whether this signature comes from a two-part protocol like an adapter signature, or actually Bob just signed the message by himself. Okay, so this is the fungibility aspect that I mentioned before. So this signature is indistinguishable from the other ones, an ordinary signature. Okay, if we now look at the properties that we expect from an adapter signature, we have three properties: unforgeability, pre-signature adaptability, and witness extractability. So unforgeability is essentially just like an unforgeability of an ordinary signature, but additionally, we give the adversary access to a pre-signature, and we assume that the adversary does not know a witness to the relation R. Okay, and we expect the adversary to fail in forging a signature in this case. Okay. And pre-signature adaptability means that anyone who knows a witness to Y can complete a pre-signature that is conditioned on that statement Y. Okay, so this is the aspect which means that basically any secretary who knows a witness should be able to adapt a signature. Okay. And then to protect the signer, we also have this witness extractability, which means that if the signer gets a hold of a pre-signature and a signature, so the signer actually already generated the pre-signature, so that's fine. And if these two are conditioned on the same statement Y, then the signer will get a witness to this statement Y. Okay, so these are the three main properties that we expect from an adapter signature. Okay, let's now look at our contributions in this paper. So we introduced the first post-quantum adapter signature that we call LAS, as I mentioned, and our construction is effectively as efficient as an ordinary signature, and in particular, the underlying ordinary signature of our construction is dilithium, which is a third round candidate for NIST's post-quantum standardization process. And our construction is based on the two well-known lattice problems, namely module CIS and module LWE. And as you might expect, the hard relation for our construction is knowledge of a module CIS preimage. Okay. And using our adapter signature, we construct post-quantum payment channel networks and atomic swaps. And in particular, our constructions do not require any additional on-chain costs other than the cost of the adapter signature. And then if I briefly mention the main technical challenges in the lattice setting, the first one comes from the fact that the proof systems underlying lattice signatures actually have the so-called knowledge gap. Okay, so I will not go much into the details, so I will actually show you in a bit what I mean by this. And then the other technical difficulty comes from the use of the rejection sampling. Okay. Right, so let's now see our extended formal model. So as before, we take an ordinary signature and a hard relation. This is exactly the same, but we also additionally need an extended hard relation that we call R prime. Okay, so R, you can assume that it's like a sub-relation of R prime. Okay, and then as before, we have these four functions, but there is two critical differences. Okay, one is that for the adapt function, this function operates properly only if the witness that you use comes from the base relation R. Okay, and the extraction function, on the other hand, gives you a witness Y prime only for the extended relation R prime. Okay, so this is essentially the knowledge gap that you get. So for adapt function, you need to use a witness from the base relation, whereas for the extraction function, you only get a witness for the extended relation R prime. Okay, and let's see how this affects the properties. So unforgeability remains the same, but we actually get a weaker notion of presignature adaptability. And in this case, as I just mentioned before, you need to hold a witness Y for the base relation to be able to adapt a presignature. Okay? Whereas for the witness extractability, you will only get a witness Y prime for the extended relation R prime. Okay? So these two are the main differences from the ordinary, let's say, or classical constructions of adapter signatures. Okay? And in this case, this means that since the extracted witness only satisfies the relation R prime, this means that an extracted witness is not guaranteed to provide adaptability. Okay? And for a unidirectional two-party interaction, this is actually probably good enough, because we can still make this relation R prime harder relation, okay, which is fine. But this may not be sufficient in the scenarios where you need to use an extracted witness to adapt or complete another signature, another presignature, okay, because the extracted witness is not guaranteed to be used in the adapt function, okay. This becomes actually problematic when we want to apply our construction in the settings of atomic swaps and payment channel networks. Okay, so we handle this in the application. So I'll tell you a bit about this. Okay, so let's discuss about our lattice-based adapter signature now. So this is an ordinary lattice-based signature, and this is like a simplified version of dilithium, which follows this so-called Fiat-Shamir with aborts technique. Okay, and this is very similar to the Schnorr's idea. You sample some randomness Y, okay, you commit to this Y and get a commitment W, you hash your public key, this commitment, and your message to get a challenge, and then you mask your secret key, which is R in this case, which is a short vector, and with this little Y, and you get a response set. But different from the Schnorr signature, you need to do this so-called rejection sampling step to make sure that this response set does not leak information about the secret key Arkin in this case. Okay, and this is our lattice-based adapter signature. I will not go through all the steps, but point out some main differences from the ordinary signature. The first difference comes into effect in how we compute the challenge. Okay, so if we have a statement capital Y, which is a vector t prime, then this goes into the hash function as an additive term. Okay, and additionally, the signer needs to check a stronger rejection sampling step or rejection sampling condition here. Okay, and then if you want to adapt a pre-signature, what you do essentially is you take the response in the pre-signature and you just add your witness to this, which is R prime in this case. Okay, and if you want to extract a witness, then you simply subtract off the responses of the full signature minus the response of the pre-signature. Okay, so here in this case, you might notice that for the adapt function, the adapter will actually use a vector with norm very small, but the difference of these two terms, the responses, may actually be much bigger than the length of the witness that the adapter uses. Okay, this is again due to the so-called knowledge gap. Okay, and in particular, if you look at our hard lattice relations, so for the base relation, the witness has an infinite norm at -1, whereas for the extended relation, the witness has norm much bigger than 1, okay, or can have norm much bigger than 1. Okay, so these two are the relations for our construction, hard relations for our construction. Okay, but note that we can still make this second extended relation hard in practice. Okay, so that's not a problem. Okay, so let me tell you now about the applications. So the first one is atomic swap. And in this case, the goal is to exchange two different cryptocurrencies while ensuring fairness, which means that either both of the parties exchange and receive the other party's coins, or none of the parties get any coins. Okay, so let's see how we can do this. So here I will tell you about the off-chain part. Okay, so there is also, as usual, an on-chain part where basically both of the users needs to lock the coins for a certain amount of time. Okay, so that part is exactly the same as before. Okay, so let's see how this works. So we have two users, U1 and U2. They have public secret key pairs, and they have some coins C1 and C2. Okay, now user 1 runs the generation function of the hard relation, okay, and gets a statement and witness pair, and creates a transaction that spends the coin C1 to the user C2, and pre-signs this transaction using the public statement capital Y that he generated. Okay, now he sends over this capital Y, sigma 1 hat, and transaction 1 over to U2. Okay, and then U2 does something similar, generates a transaction TX2 that spends the coin C2 to the user U1. Okay, and then again pre-signs this transaction using the same statement capital Y, and we get a signature or pre-signature sigma 2 hat. The transaction together with the sigma 2 hat is sent over to U1. Okay, and then since U1 knows a witness for this relation, especially for this statement capital Y, can now adapt this pre-signature sigma hat 2 and get a full signature sigma 2. Okay, if everything goes well, U1 publishes sigma 2 on the blockchain to claim the coin C2. Okay, and as soon as sigma 2 is published on blockchain, this means that U2 gets access to sigma 2, and since she also has access to sigma hat 2, which is the pre-signature, she can run this extraction function to get a witness Y prime. Okay, and then she will use this witness Y prime to adapt the first pre-signature sigma hat 1 to get a signature on the first transaction so that she can claim the coins C1. Okay. And actually, there's a problem here, as you might also have seen. Here, U2 is using an extracted witness to adapt a pre-signature. Okay, but we have said that our construction actually does not or only satisfies a weak notion of pre-signature adaptability, which means that this Y prime is not guaranteed to be able to run a proper adapt function. Okay, so to circumvent this problem, we need to do more, and we will actually ask the user U1 who generates the witness and statement to also generate a proof that this witness, which is little y, actually satisfies the stronger notion of the infinity norm, which is basically saying that, or he basically proves that this y that he generated comes from the base relation. Okay, and then he sends this proof over to U2, and U2 verifies this proof and also the pre-signature, of course, and only if they verify, U2 proceeds to the next steps. Okay. Now, if we do this, we can actually show that this protocol is fair because this function is essentially the relation that we have is essentially Lattice hash function, and this is collision resistant. So this witness y prime has to be the witness generated in the first place. Otherwise, this violates collision resistance. Okay. And to briefly discuss about the fairness, this is quite easy to see. If U1 aborts at some point, which means that sigma 2 is not published on blockchain, then U2 basically does not get anything, and both parties do not get the coins. So this follows from the unforgeability property. And if U1 does get the coins, which means that sigma 2 is published on blockchain, then of course U2 gets a hold of this signature. And since she also has the pre-signature that corresponds to the full signature, she can run the extraction function, get a witness, and use it to adapt the first pre-signature sigma 1 hat. Okay, but of course, as I mentioned before, this proof pi here is crucial to ensure fairness. Okay, so for the payment channel network, so in the paper we first construct this so-called anonymous multi-hop payments that is due to Malavolta et al. From NDSS last year, and then the payment channel network itself follows from this construction. Okay, so I will refer you to the paper for the details of that construction. And these are some of the references that you might have a look at. And the full version of our paper is available on IECR's ePrint. And please feel free to email us your questions if you have any. Thank you.